All right. Hi, everyone. Here's the second part of this video. We're going to be trying to prove various properties of functions using formal definitions and formal proofs. So last video we talked about whether or not functions were injective and trying to prove that. This video will naturally focus on surjectivity. Remember, surjectivity, the other common word to describe whether or not a function is surjective is we can say a function is onto. And it's up to personal preference which one you use. I like surjective. I also use onto. Absolutely up to you. This was when we first saw the definition of surjective. So a function where the domain's name is x and the codomain's name is y. It's surjective if for every element of the codomain, which we'll call like little y, we can find or there exists at least one element of the domain, which we'll call like alpha, where f maps that alpha to that little y. So every single element of the codomain gets mapped to in some way. Like before, like last video, let's go ahead and take a look at a couple examples just to get us warmed into to warm us up a little bit. Let's try to decide without formal proof, but just by inspection. Let's try to see if any of these four functions is surjective. And for number two, I went ahead and gave a composition, so we can answer the question for each of these three functions. Okay, so if you want to pause the video and try to answer, I'm just going to go ahead and go right into the solutions. So this first one is yes. Oops. First function is surjective, yes. And the reason why is because we can just go through each of these three elements in the codomain and say, yeah, there is something that maps there. And that's all it is. So yes, it is. Number two, f is not surjective. And the reason why is because there's an element of f's codomain, which is we're calling y. So the kind of third element here in the codomain, there's no arrow pointing from x to go there. So there's no way to use f to map an element of x to this particular element. So the answer is no. G is because G's codomain, Z, has three elements, and each of those three elements is getting mapped to from y in one way or another. So you may know, if you're comfortable with injectivity, you could mention that G is not injective, but it is surjective. So it's not injective because these two elements both map to the same place, and that breaks the law of injectivity. But it does happen to be surjective. Okay, for the composition, our domain is x over here, and our codomain is z. So we take this first element, apply the rule given to us by f to it, and then apply the rule given to us by g to it to get from x to z. So this function, although there are arrows ending up in all these places in z, there's actually no way to get from x to this second element because there's not a way to get to the only element that maps there. So this first element goes to the first element of z, second element of x goes to the first element of z, and the third element of x goes to the third element of z, but nothing goes to the second one. So the answer is no. Number three, this is the same function that we looked at in the injectivity video, very complicated, or I should say relatively complicated piecewise function. It is not surjective. And there's a couple reasons you can look at, but because the codomain is all real numbers, we would have to say that any single real number we could think of, there's a way to map to it. So it looks like all the negative real numbers are getting mapped to, although we're only drawing a part here. I could say like negative 100, and you can figure out that you could figure out an x value that maps there. Just like a random example, but there are a couple various elements of y that we could find here that we would just cycle through each, or we would look at each one of these and say, okay, there's no value of x that would correspond to it. So in particular, you could say 6 is an element of the codomain, but for all, I'm getting a little bit ahead of myself. This would be like a formal statement of the counterexample. But for all alpha in the domain R, applying the rule given to us by H to that alpha doesn't result in 6. So this, like up here, there's nothing. The graph will never give us a y value that equals 6. And that's not the only one. Another one would be like 1/2. So just looking at this and explaining, looking at trying to come up with the equation like negative x squared equals 1/2. This has no solution. If we look at the second case, 2 plus cosine of x equals 1/2, that's going to have no solution because cosine is going to be, the output of the cosine function is going to be bound between 1 and -1. So that wouldn't work either. And then for this other one, again, you could use some like just understanding of how exponential functions work and say that this would require us, because e to whatever power is always going to be a positive number, blah, blah, blah. I'm just going to write ... there. There's going to be no value of, okay, whatever. There's going to be no value of x that's going to give us a negative value for e. So that would be impossible too. Again, I'm kind of slipping into a formal statement of the counterexample, but just by inspection, you can look at this and say, there are some values of y that we'll never get to, that we don't have a way to map to. Okay, this last one. Again, same codomain. All real numbers. And yes, it actually is surjective because even though it fails injectivity at points like this, it does look like it does look like no matter what, we could figure out at least one x value that would map to any element here. So various ways to do that, but you could just take like this will make more sense later, but just as an example, getting into it, you could pick this y value and then kind of set up this equation and then try to solve for x. And it's basically whether or not this polynomial has a real solution, where in this case we're considering y to be like a fixed number and we're trying to solve for x. So this would be like a constant. We're just basically trying to look at this polynomial equation and say, okay, are there any x solutions to that are real numbers? And the answer is yes, there will be. So okay, going on then. Here's the first example. Let's actually try to formally prove that a function is surjective. So let me just go ahead and copy the definition of surjectivity. So f is surjective when, or what surjective means is for all elements in the codomain there exists some alpha. I generally like to use alpha instead of x, just so I don't get confused with the rule. I'm not trying to say like I'm just saying like alpha being like some particular value. It's not a variable really. It's something that's going to be dependent on what this y is. So that's if you're wondering why that is. Not all definitions of surjectivity do that, but I just think it makes it a little bit clearer if it's your first time working with proofs like this. So I'm just calling the particular element we're looking for alpha rather than x. And again, no real reason to. It's a little bit clearer to me. So can we find for all elements of the codomain, does there exist some alpha where f of that alpha gives you that element y? So just looking at this really quickly, this is a line. Recall that this x maps to 3x minus 5 is just shorthand for saying, or it's an alternate way of saying f of x equals 3x minus 5. And it's completely up to you. But it's good to be familiar with both forms of notation. Looking at a graph really quick, you don't have to prove this graphically, but I think it's a good idea if you can visualize it. Not a bad idea to try it. With a positive slope in some way. The graph of f is going to look something like this. Pretty convincing already that it will be surjective, that there will always be some value for any real number. But let's just go ahead and formally prove it. So we're ready to get kind of started right away. Or I guess here, before we get started, it's kind of nice to do a little pre-prep. So when you actually do the formal proof, it's clear really what the steps are. So let's go ahead and do let's go and do like a little prep work first. So we'll call this like scratch work. We are going to take an arbitrary y here, y of the codomain, and we want to figure out our goal here is to find this alpha. I mean, of course, we want this alpha. I mean, f of alpha is going to be 3 alpha minus 5. And we want it, our requirement is that this thing equals y. So, of course, that gives us y equals 3 alpha minus 5. And doing this, we can solve for alpha. So we'll get y plus 5 divided by 3 equals alpha. And yeah, that is going to be a real number for like this fixed value of y. We will get, you can always, whatever real number you have, you can always add 5 and divide by 3, no problem. So alpha will be our particular value that gets sent to this arbitrary y. So I do like to separate that just so it's a little clear when we do the proof. It'll be a little bit clearer kind of what our logical flow is. So let's take a look at it. So starting here, prove that f by this rule is surjective. So take an arbitrary y in the codomain. Then let's go ahead and call this, let's go ahead and define this. I'm drawing the define symbol backwards here. But we'll go ahead and call this, we'll go ahead and call that alpha. That alpha is an element of the domain. Sometimes you can call, you might see this notation where we're talking about the domain of f. So that alpha is an element of that is a real number, so it's going to be an element of the codomain. So with that choice, so we could say like then let, and define alpha like this. Then f of alpha equals and then we just plug it into the function and demonstrate that it does what we want it to do. And then obviously. So again, because it's our very first proof, maybe we want to just summarize here. We are actually already done. So for any arbitrary y, we can find an alpha given by this rule such that f of alpha equals at y. Thus, by definition, the function f is a surjection. And we're done. So that I mean, I would not end the proof here. You could say, therefore, this meets the definition of surjectivity, or so we found f of alpha, or we found an alpha, so f of alpha equals y. But just do have some sort of summary of it, at least at first, just to kind of convince yourself and convince the reader, yeah, okay, I did meet the definition exactly. Since our choice of y was arbitrary, we can always find an alpha that maps there. Therefore, it's a surjection. Perfect. Okay. But yeah, that's it. Very short. Okay, so number 2, or example 1, I'm calling it, is x that maps to this a surjection? Prove or disprove? So I want to not graph this right away. If you think about the graph of what this would look like as a graph, yeah, you might be able to see the answer right away. But I want to show you what happens if you try to just follow the steps of proving something's surjective if you're not careful. So I'm going to call this, so be careful. I'm going to call this an attempted proof. Okay, so we want y equals for some arbitrary y in the codomain. We're going to try to find x, so what we can do is square root both sides. And then we'll get alpha plus 1. Something wrong happened here, but we'll talk about it in a little bit. So then that would mean alpha equals, rearranging this equation, we can get alpha equals, sorry, this should be square root of y minus 1. So we go, oh, look, we found our alpha. So then you could say, so for any arbitrary y in the codomain, pick alpha equals square root of y minus 1, then f of that alpha equals minus 1 plus 1 quantity squared, just using the rule of f, equals, okay, looking in here, we would get square root of y quantity squared equals y as desired. And then that would be our proof. Okay, the problem is that this is wrong. And the reason I'm doing this so soon is I just really need you to be careful for surjection, for proving things are surjective. You have to make sure that what you're doing here makes sense. You should be familiar that maybe, okay, noticing there's a there's a problem here. If we take the square root of both sides, we need to throw in a plus minus somewhere. So, or maybe let's throw it in over here. And you go, okay, well, that could be the issue. But it doesn't matter. Now it looks like we're given two choices for y, right? So that's not really the issue. the issue isn't really that we need to throw in a plus minus. It's actually something more fundamental than that. Pause the video and see if you can see what the problem is, because this function is not surjective. If we look at the graph here, f of x is quantity x plus 1 squared. So this is going to be a parabola, different color. This is going to be a parabola with the vertex at -1, 0, and it's going to look gross. I don't know, it just needs to be bigger. Nah, whatever. I can draw a parabola, I promise. Okay, it's going to look something like this. So it's not going to be surjective because there's no way to get to negative numbers. So why does this proof look like it works? What's the problem? So pause the video and see if you can see. But, okay. Let's go ahead and get right into it. Here's the issue. That. This is not defined if y is negative. Y needs to be absolutely arbitrary. So what we're doing here needs to work with that arbitrary choice of y. And I mean it's not defined. By that I mean specifically it's not a real number, right? If we take the square root of a negative number, we're going to get a complex value. But what we're looking for here this alpha that we found here is actually not going to be an element of the domain. If y is less than 0, we'll get a complex number instead. But f is supposed to be not mapping from complex numbers to r. It's supposed to be mapping from real numbers to r. So alpha is not a real number. So this whole proof does not work. Now, if you want to, let's see. If you want to actually try to figure out how to disprove this, all we need to do is pick some value of y and show that you can't get there. So what we can do is take a particular choice of y. You could say y being anything less than -1. You don't really get any benefit from being as general as possible. You can just take a particular choice and just show, okay, here's a particular element. Y is an element of the codomain. Maybe you could say like, so y is an element of the codomain. And but you could say, but for all alpha in the domain R, f of alpha would give you this equation that we would need to satisfy. Oh, sorry, this should be an alpha here. And then you could just argue that this equation has no real solutions. So picking one particular element of the codomain, we have to say all elements of the domain will not give us that value. They'll map to something else. So therefore, F is not a surjection. And again, our choice of -1 was just to pick something simple for convenience, but this would be true of any negative number. So there you go.